And the other generalization is fixing the spin. We could have chosen different probes to measure our state that is flowing. Okay? Very good. So, yeah, I think this general construction that I showed yesterday of these flat connections and so on would deserve a more detailed discussion of how broad it is and so on. But given that we are coming back to it at some point, I will postpone a more broad discussion of this general framework to when we revisit that within the context of string theory. For now, we understood what we wanted to understand. We had this nice blackboard with a complete logic yesterday, so I think I will leave it at that. Any other questions before we start the official lecture? Okay, it starts now. So, I want to start, so today, as we said, we are going to be, today serves more as a motivation lecture between two parts of these lectures. And basically what I want is to motivate, the goal is twofold, is to motivate kind of a philosophical claim that I will make now. And the second thing is to introduce an important concept in theoretical physics, which is the large N 't Hooft expansion. Okay? So who has seen the large N 't Hooft expansion? Have you seen it before in the lectures? This large N expansion? You have? Yes? No? Can someone? Who did not see it in the lectures? Can you raise your hand? If you did not see in the lectures the large N expansion of 't Hooft? So, okay, so it was not in all the lectures. It was in some optional lectures. Okay, so I'm still going to explain it. So let me present the claim. And the claim is that large N gauge theories okay, N being the number of colors. So gauge theories where gluons are N by N big matrices and quarks are N big vectors. Okay? So large N gauge theories are, and if you want, you can insert here some cautionary words, like in some sense, more or less, whatever you want, if you want to make the statement correct by definition, but empty. So large N gauge theories are string theories and / or spin chains. I want to show that in general, these objects are not so, there ought to be some connection. We are going to be vague today and resume being, and become much more precise tomorrow, but for today, we just want to hand wave and to claim that there must be some connection between large N gauge theories and spin chains or string theories. Okay? So let's try to arrive at this claim to justify it. And to do it, let's illustrate these ideas with the simplest possible set of gauge theories. These are theories called matrix models. So let our discussion be centered around matrix models, which are models for where you have a matrix M. So this M is an N times N matrix. Okay? And what we are doing is, in our theory can be defined by saying that if you want to compute a given observable, you should integrate over all possible matrices e to the minus some action times whatever you want to compute the average, and you normalize it such that average of 1 is 1. So what is this S of M? The action is there is some kinetic term. Okay? There is some kinetic term, and then there is some potential, which we can write some cubic interaction plus some quartic interaction. And all these T3, T4, and so on are couplings. These are called couplings. So this is what we call a kinetic term. And these guys are couplings. Okay.
What's the relationship, or is there a relationship between this and like rubber things?
No relation at all.
No relation.
Nothing to do. To my knowledge, at least. Very good. So there is a kinetic term. There are some couplings. Okay? And there is a measure. Okay? Now, the measure depends on what kind of matrices you are. For example, if we have Hermitian matrices, we would say that this would be, we would have to integrate over the diagonal elements of my matrix, but also integrate over the off-diagonal ones. And if it's Hermitian, I can integrate over the upper ones. The other ones are just complex conjugate. So I integrate over the real part of Mij. And I integrate over the imaginary part of Mij. Okay? The Mii are real. Okay? So this will be for the Hermitian matrices, for example. Now, why is this related to large N gauge theories? Because this you can think of as gauge theories in 0 dimensions. Okay? So these matrix models, a fancy way of calling these matrix models is saying that these matrix models are nothing but gauge theories in D equals 0. Namely, you have a theory, but there's no space-time. There's no space or time. Space-time is a point. So these matrices, they don't have a label of space-time because space-time is just a point. So there is no dimensions. And we see it's a gauge theory because you see there is the symmetry under M goes to omega times M times omega minus 1. At any point in space-time, which there's only one. So, okay, calling it gauge or global symmetry, it's a bit arbitrary. It's your choice because there's only one point, but definitely we can call it gauge symmetry, so why not call it gauge symmetry? It's fancier than global symmetry. Okay. So this is a symmetry of our 0-dimensional gauge theory. Okay. Now, why do we consider, so, just one second. So, the only difference, if I would consider a model, a general model in D dimensions, so in D dimensions, I would replace this. So in D bigger than 0, what would I write? I would write something like a Laplacian of M squared, a derivative of M squared. Right? I will just put a kinetic term there. Now, I want to emphasize that all I am going to say could be done if I put a derivative there, because what we are going to discuss is related to the matrix nature of this object. It doesn't care whether the graphs I'm going to draw, I could attach to each vertex a space-time point, a space-time position, and it would only complicate and decorate the discussion by having space-time dependence everywhere. But what we are interested in is just in the large N dependence, is in the matrix structure, is in the index structure of these objects. So I'm simplifying my discussion in going to D equals 0, but all the conclusions should be valid in any D. The only difference is that in D equals 0, the propagator is very simple. The propagator between matrix Mij and matrix MKL, which you have to compute. You write the kinetic term, you work out the propagator, right? The propagator is just the inverse of the kinetic term. It's not as trivial as you might think. You have to, this is the measure, you write trace of M squared as Mij, Mjk. It's a quadratic term, you integrate, you compute the propagator. In fact, it's part of today's tutorial. And you get that the propagator is the inverse, and because we normalize it with a coupling in front, the inverse will put a G string upstairs. And then there is a delta IL delta JK, which I can draw as saying that I have my matrix, and my matrix, I think of it as an object with two indices, one index being I, one index being J, and then index I goes to L, index J goes to K. So this is what's called a fat propagator. So I could draw it just as a line. Okay? And just as a parenthesis, in d bigger than 0, we would have similar story, trace of mij of x, m k l of y would be equal to the same thing, but then there will be some scalar propagator, some scalar dependence on the position x minus y. And these kind of propagators would then dress all our conclusions and just make our expressions nasty. But what we are interested in is really in the matrix structure, in all these Kronecker deltas, how they contract, and so on. And this is, again, why this space-time dependence is totally irrelevant for our discussion. Okay?
So are you gauging out by the symmetry?
Sorry?
Are you gauging out by the symmetry? Are you treating it as a gauge symmetry or a global symmetry?
It doesn't matter. This model has this symmetry. So
You need to divide the measure if you treat it as a gauge symmetry.
So let me try to see if no. I'm doing this like in a gauge theory. But however, you are right that there are observables that, what are the right observables in this theory? What should I compute average of? I should compute averages of gauge invariant operators. Okay? So it's true that here, the natural gauge invariant observables contain, for example, natural observables would be trace of the matrix to some power, for example, because this is invariant. And when I compute average of, say, trace of matrix to some power, in practice, this integral doesn't depend on the angular dependence of the matrix, but rather only on its eigenvalues. Because trace of a matrix to some power, just sum of the eigenvalues to some power. And similarly, if I write M as a diagonal matrix times some rotation matrices, the rotation matrix also drop out. So the only thing I have to do is understand how this measure reduces to when I go to the dynamics of the eigenvalues. But it's true that secretly there is a big redundancy, and in these matrices there is the diagonal part, which is the interesting, juicy part, and there is all this angular part that in principle we don't care. So gauging it away would mean, indeed, going to this language of eigenvalues, which will know should be more efficient, because instead of having n square variables, we should be able to reduce this problem to just n variables, which are the eigenvalues. We could do it. This would be useful to compute this. But as a definition, it's good as it is. Going to the language of eigenvalues would be gauging it, as you are saying. Okay? But it's like in a gauge theory. We write a gauge theory, then we start putting Fadeev Popov and so on to make the computations more efficient. But we start, and we have what we have. Okay?
Couldn't we have a term with division integral?
We could. Yeah, nature could be this, could be determinant of M. Yeah. But M would not be good. Computing average of M is not very reasonable. It's not gauge invariant. M transforms. But yeah, determinant of M, trace of M, eigenvalues, spectrum of eigenvalues of M, these are all good observables. Okay. So now let's compute. Let's start by let's use this notation and see and let's consider an example. Let's compute the expectation value of an operator trace of M to the 4. And I will always normalize my operators in the same way as I normalize the action. I put a 1 over G string in front of the operator. We will see that this is a nice normalization. Okay? So this is my operator O. It's a local gauge invariant operator. Okay? It's a trace of something. So people call these operators single trace operators. It's a single trace operator because it okay. So let's compute the expectation value of this object here. So what would this be? Okay? This is the expectation value of 1 over G string. And then let's write explicitly what this M4 means. It means that I take my matrix Mij, I multiply Mjk, multiply again Mkl, multiply again ml and another index, but I take the trace, so that other index is I. Right? So this is what this object means. And now how do we compute this expectation value product of 4 of these guys? Well, we use weak theorem, right? We have a Gaussian action. We have a propagator computed here. And now I just contract this guy with this guy, this guy with this guy, or this guy with this guy. Is it clear? So now I just do all possible weak contractions. Okay? So now this guy here, before doing that, let me just draw a picture. How do we think of this guy here? If we think of this in this way, what is this object here? So I have my index ij, and then let me draw it and then put the labels, and then it will become clear. So we have here our index ij. As I specify this, now the rest is clear. You see, j goes here. After j, we have k. After k, we have l. And after l, we have I again. So this is how I think as my vertex. It's a fat vertex now. Okay? And now I have to contract. I have to unite this by propagator, start drawing this propagator. So now there are only 2 options which are distinct. When I have to connect this, so look now, pay attention so that you see the combinatorics. When I contract this guy, I either contract it with this one or with this one, but that's the same, means I contract 2 neighbors, or I contract to the opposite one. So there is 1 option for contracting with the opposite one and 2 options to contract with neighbors. Okay? So this is equal to 1 over G string, and then there is a factor of 2 if I contract with neighbors. So let's write M I L M L K, and then the other one M I J M J K. Okay? Or if I contract with not neighbors, I am I J M K L times M sorry. M I J M L K, and then M J K M I L. Okay, can you read? I'm sorry, it's too. Good. So now let's compute what happens here. Each of these propagators gives a G string. So in total, I get, let me write here, this is equal to 2 G string, this G string square cancels one of these G strings, and then this propagator, so let's write it explicitly, delta IK delta LL. Okay, this is one propagator. The other propagator, delta IK, delta JJ. And then the second term, plus G string. And now we get delta IK, delta JL, delta JK. No, delta JL, delta KI. Okay? Which now we compute. So what is delta LL? I sum over L, that gives N. What is delta JJ? I sum over J, I get N again. So I get N squared here, and then I contract K with K, I get delta II, which I sum again, so I get N cubed. Okay? So all this stuff here gives me N cubed. Whereas this one here gives me N. Because I just contract all the indices. You see, this gives JL, then, I did something wrong here. J, L, K, I. The first propagator is, there's something wrong here. I, J, J, K, K, L, not L, K. So it's K, L. So here it's K, L. What's going on? Sorry, don't copy it right now yet. I, J. Okay, let's do it properly. So let's see. So we contract neighbors, so we get I. Okay, my problem is, okay, good. Okay. I, J, J, K. These are two neighbors, and the other neighbor should be K, L, L, I. I was just reading the graph and misinterpreting left and right index. And then let's look at the formula, which is safer. M, I, J, K, L, that's good. And then J, K, L, I, not I, L. Okay, so now let's rectify the formula. L with L is good, I with K is good. So this was good. I with K is good, J with J is good. So that was good. But now here, I with L, that was wrong. J with K. And next, J with I, also wrong. K with L. Good. So now you can see it's N because I, L, L, K, so it becomes I, K, then becomes J, I, then it becomes J, J, and then it's just N. Okay? So we see that we get this. And now the point is that we can see that what were we doing? Let's now draw a picture and see what we were doing. We got 2 times the following thing, times this graph where we contract neighbors, right? There is this 4 vertex and we contracted neighbors. And we saw that this graph gave n cubed. Okay? Times G string. Plus 1. 1 is not important, but what's important is that now we have the case where the lines that are contracted are not adjacent. So if I draw it, I get something like this. And this guy gave me G string times N. Okay? So we see that there are some graphs that are more important than others. And let me point out what is the difference between these two graphs. The difference is that the first graph, I can draw it on a sphere. I can put a sphere, and I just put my graph here. Whereas to draw the second graph without lifting the pen, you see this line goes over here, I cannot draw it on a sphere. I can, however, draw it on a torus. Let's do it. Let's consider a torus. And you see what I can do. I have my 4 vertex here. And this line connects with this line. This line connects with this line. Okay? And now these two connect, and that's fine. They can just go around, wrap this donut. And connect. Yes?
Is there any difference between drawing on a plane and on a sphere?
No. So this graph here is called, in fact, this graph, they are even called planar graphs, you see. It's kind of highlighting precisely that it's the same, putting on a plane or putting on a sphere. If you can draw it on a plane, on a sphere, you can, of course, just remove a point on the other side and open it up, and it's a plane. Whereas these graphs here are called non-planar graphs. In this case, we would say it's a genus 1 graph. It's a graph that needs a torus, an object of genus 1, to be drawn. And what we are seeing here is that these planar graphs, they are much bigger than the non-planar graphs when n is very big. Of course, it could be a coincidence. We are just working out one example, but I will now claim that this is a general feature. So because what is happening? You see that this power of n cubed, we don't need to contract all this delta function doing typos as I was doing to arrive at it. We just draw the picture and count how many loops of color we have. So let's count here. How many loops have we have? We have one inside, one here, and one outside. So 3 loops, so n cubed. Right? Just counting how many loops we have. You think that this is like frames, and we are putting glass windows here. How many glass windows you need? You need one here, and one outside. Okay, so how many loops you have? N cubed. Immediately you see. Whereas here, if you follow this line to see, you follow this line, it goes here, 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 here. You went back to the same thing. So there is only one loop. So there is only n. So the point is that when graphs are planar, they have many more windows. When they start being non-planar, you can just put a single frame, for example, in this case, a single window, and you can, that ends on this frame. Okay? So these graphs are this thing here that we obtained was, let me write it.
So is that n goes to infinite the same n as this, the number of mirrors that we are putting?
Yeah, the same. Yeah, this n is the number of colors. This is how big these matrices are. So just give me 1 second. I'm a bit confused by something here. What was the problem? Okay. So this computation, let me write it in the following way. Let me say it's n squared that I factor out because I want to. And then let me write it as 2 lambda plus 1 over n times lambda, where lambda, this lambda, it's an important object, is defined as the product of this G string times n, is called a 't coupling. Okay? So this is called So this is just a statement, and now let's fit this into a broader framework to see what should be the general picture.
There should be an n squared somewhere, right, in the second term, because,
I hope not.
well, you got n squared times 1 over n times lambda.
Good point. So indeed, n lambda, this gives just G string, n square. Good point, yeah. Indeed, as we saw, the difference between these two terms was n squared. One term was bigger than the other n squared. Another type? No.
Just a more, I guess, just before you move on, I want to get my head around this. When we I'm used to seeing, propagate these expectation values if I'm calculating out, because the probability of finding a particle over here at some later time was over here at this point in time. But here we're looking in 0 dimensions. What are these correspond? Like, what are these things we're calculating correspond to? What's the physical significance?
So for example, suppose I sum over all graphs like this, which are graphs that don't have external x.
Okay.
I would be computing the free energy of this quantum field theory,
Okay.
where I sum over all bubble diagrams. And this is one bubble diagram, another bubble diagram. I would sum over all of such graphs.
Okay.
But I want to highlight again that the point is that all these things that I'm working with 0 dimensions, I'm working with 0 dimensions because I don't want, you see, what would change if this was not an analysis at 0 dimension? It would be that now it's, instead of lambda, for example, this is lambda times a propagator here times another propagator here. But from the point of view of saying that this is much bigger than this, it doesn't affect anything. So I just don't want to have propagators all over. So that's why I'm putting 0 dimensions. But the conclusions are not the same, are the same. So don't, I would not pay too much attention to the fact that we are in 0 dimensions. What's important here is that we are dealing with matrices of big size. So let me give you another example. Okay? Another example would be, let's consider a correlation function of two operators now. 1 over G string trace of M cube, and the other operator, the same thing. 1 over G string trace of M cube. Okay? So this, you would say, is related to the expectation value of one operator times another operator, which I can also represent, let me tell you, because this is going to be used a lot. I can also represent one operator like this, provided I indicate clearly that this is one operator and another operator like this. See, here I'm just highlighting that an operator has 3 legs coming in, and if you follow the lines, you can read off the indices. Okay? So, of course, this is the most natural one, but I can also draw it in that way. It's just a question of drawing. I should, of course, keep in mind that this is not, this part here is not a propagator, of course. It is just a notation to indicate exactly the same thing as this, but just sometimes it's convenient. If you have like a vertex with 10 legs, for example, this is much easier to draw than to make sure you draw a star with 10 legs. It's often useful to use this notation, which is simpler to not to make a mistake. Is it okay? Just notation. Okay. And now how do we start computing this object? Well, we will start computing it. So let me use the last notation. And let's draw a few graphs that would contribute. So the simplest one, I have my vertex. And I just connect them. I just connect this by a propagator, this by a propagator, and this by a propagator. Okay? Then I could imagine having another example where these guys interact with each other. This is if I start pulling down from the action some of the interaction vertices. For example, I could have this. Okay? This is bringing down from the action 2 cubic vertices. Okay? If I bring down from the action 2 cubic vertices. Or I could bring down from the action a quartic vertex, in which case I will draw, for example, something like this. This would be bringing down from the action of vertex. Again, let me emphasize again, the first and last lines are an operator. These are not vertices or propagators. This is just a notation for this star that we are just choosing to draw it like this because I find it simpler to draw. Okay? Perhaps to highlight, we can do the following. You can put some yellow ball to separate it from the rest. I don't know. If it helps, put it. If it doesn't, leave it. Yeah?
So the second and the third picture,
yeah.
All the lines are connected in the same way, but you kind of like, by bending them, you merged 2 vertices into...
That's right. So topologically, they are very similar, these 2 graphs. Okay, but so this is using, this graph, for example, would be proportional to T3 squared. It would be using 2 cubic vertices from the action, whereas this graph would be proportional to T4. It's being a quartic vertex from the action.
So we could have more different, yet topologically same...
Oh yeah, for sure. And that's what I'm wanting to highlighting in this picture. So all these graphs, where this is the incoming operator, this is the outgoing operator, and so on, all these graphs have the same share a characteristic that they can be drawn on a plane. So this is one family of graphs. But then on the second line, we could draw graphs that fall in the different category. They could be graphs where, for example, this line goes here, but these 2 guys decide to send a particle that passes below the other one. Yeah, I could have something complicated like this, for example. Okay? Whereas now, because this line goes through here, this one I cannot draw on a sphere. Okay, plus ... Okay, so when I compute all my Feynman digraphs, I can isolate them and separate them by in which topology can they be drawn. Okay? And now, just as a cartoon, the claim, and we will now see that this is true, is that I can think of these kind of objects as saying that they all have the following topology. What is the topology? They can all be drawn on a sphere with two insertions. So I have one insertion here, one insertion here. So it's like a sphere with 2 points removed. What's a sphere with 2 points removed? It's a cylinder. Right? I remove 2 small circles of the sphere. Now it has the topology of a cylinder. Right? I start with a circle, evolve it, go back to a circle. Is it clear? So all these graphs, topologically, I can think of them as a cylinder that is evolving to another cylinder. And I'm drawing some wavy stuff to indicate that I sum over all such graphs. All such graphs over this topology. Whereas these ones here in the second line, they look like you have 2 punctures again. And you also sum over things. But in the middle, there is 1 hole. And then there could be a line where there are 2 holes and so on and so forth. Yes?
Did you say that the second line diagram doesn't go on a sphere?
It does not.
Oh, I didn't
It's
see it quite
similar.
right. Yeah.
It's similar to the one there. You need to put on a torus. If you put on a torus, that's fine. You put all except this line, right? This line here going here goes on one of the cycles of the torus. The other ones go all in the front. Okay? Yeah.
And what would be something that has genus 2?
So what would be something that has genus 2? So let's try to draw something that has genus 2. In fact, probably the simplest. I did not do this exercise. Let me try to do it right now. So let's draw something with genus 2 here. Something that here we know needs to be drawn on genus 2. And then let's convert it, what would be the graph. So what would be? I just put something here, right? And then I put something here, for example, and then I unite them, right? So I think this needs to be drawn on genus 2. Right? Am I right?
No, I mean, there's no reason why you can't connect those 2 holes, right?
Sorry?
There's no reason why you can't connect those 2 holes, right?
Connect those 2 holes.
You can have 1 hole and both of them going
Yeah,
around.
like just have 1 hole. But
Yeah. Okay.
I
So,
think you need to make like the connection between.
okay. Now I cannot draw them on a. Right? So now let's see what this corresponds to. So now let's draw it here. So I have this thing. This line goes here, then it goes up, then it goes here, then there is another vertex. Then this line goes here. No, not like this, sorry. This line goes here and interacts here. And then this line will go here. This line will go here. And this line will go here. And this line will go here.
There's some kind of argument about like calculating the Euler characteristics.
There will be, of course, yeah. That's what I'm going to do now. But let's now just, given that we did this example that was so tough, let's take some advantage of it. So let's see what would this contribute to concerning powers of n. So let's start counting powers of n. We'll start counting a loop. We start here, we go here, 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 here, here. I'm just seeing how many loops there are. Here, 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 here. There's only one power of n. Okay? Yes?
Can I ask the first
Yes.
statement? Why do we need the 2 points to be removed? Why can't we just draw it on a sphere? And then
No, we can't draw it on a sphere, but I want to consider correlation function of 2 operators. So the way I think is that each operator is like an insertion, a point marked on the sphere. So it's a sphere with 2 marked points. which is the same as a cylinder. It's like, you imagine like in string theory, when you have a sphere and you insert two vertex operators at 2
How
points.
would you draw that diagram on the cylinder? The very first one.
This one, how would I draw it? Where? On the sphere?
On the cylinder? Or do you draw it on?
Yeah, I'm drawing it on the sphere. I just put a sphere here and I draw it on here, but then I say these 2 points are like, if I remove those 2 points from the sphere, then it looks like a cylinder. Okay. Okay, this diagram goes like n. Okay. And what I want to emphasize to say is the following. Let me see if I could do it. Okay. And we can, and the claim would be that if I remove this, okay, so the claim is that without this, it would go to n cube. And it will be more important because without this, it becomes of different topology. So let's see, can we see it or it's too hard? So if I don't have this, let me try to do it now by head. So the line goes here, 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 and here. Yeah, there is one here. Right. So you see, remove this propagator. Now just connect them. Sorry, how many loops do we have? Let's start counting here. If we start counting here, we start here, go here, go here, go here, go here. So we went back to the same thing. So this starting from this line, you would get 1 power of n. If we start here, it's a, no, this one was the same. So this was 1. You count just 2?
It's on the left, yeah, just the second one's on the left of the...
Okay, so without this, it would go to n squared. You are right. But then we will have to count, but let's be more rigorous, and let's count powers of G string as well. Okay, let's count powers of G string. So first of all, does everyone see that it's n squared? Because you start from this point, you go around like this, right? You start from this point. Now I cannot see. Ah, yeah. So there is one loop that corresponds to the line, this line here, and one loop that corresponds. So this guy go like this, like this, like this, like this, and like this, and one to the inner line, right? And one to the inner line. So one loop is the outer line, one loop is the inner line. And that would give n squared. Is it clear? If we remove that line. But now let's see powers of G string. So right now, how many powers of G string we have? Well, this is quite a tough example that we chose. I don't know why, but okay. So how many powers of G string? Let's first count propagators, because each propagator comes with a power of G string. So let's count propagators. We have 1, 2. Wow, this is going to be very tough to count. Let's try to count. So 1, 2, 3. Then this one from here, 4. The one that goes from this point to this point. So 1, 2, 3, 4. These are okay. And then there is this one here, 5. And this one here, 6. So G string to the power 6 from the propagators. Okay? How many vertices we have? 1, 2, 3, 4 vertices. Do you agree? 4 vertices. Each vertex gives 1 over G string, right? It's how it is in the action. So 1 over G string to the 4. Okay? Now let's do this without this line here. Without this line, now this is at least easier. Because without this line, we lose 1 propagator. So instead of G string to the 6, no, we lose, it's not that easy actually. So, because I miscounted propagators, didn't I? Yeah, the number 3 should be 2 propagators, because there's 1 propagator from here to here and 1 from here to here. So there's actually, let's say, 3 and 7. So there are 7 propagators. Now, when we remove this line, these two propagators become just 1, and these 2 become just 1. So I lose 2 propagators. So I get G string to the power 5, plus the one I'm cutting out. So G string to the 4. and vertices. I lose 2 vertices times 1 over G string square. Okay. At least I will know in the end if the result is correct or not. Don't worry. So, and then, so what is this? I want to factor out n square because that's how we decided we are going to do. So this, let me write, I factor out n square. And after I factor out n square, I have G cube, which when I convert to lambda, I get lambda cube over n cube. But because I have n square, 3, 7 cube, I have n here, n square, n to the 4. Whereas the second one, I factor out n square, so I get n square. And then I get G square, which is lambda square over n square. So what is the conclusion? Is that, like here, if what I hold fixed is lambda, one term is much bigger by the other by 1 over n square. So it's a clear pattern. We increase the genus, we lose n square. Okay? So this term, okay, this here is this guy here is much bigger by this by n square. And they differ by genus, by 1 unit of genus. Okay? So now let's see that this is a general pattern. So now let's prove that this is always the case. And doing the general case is much easier than doing this two-loop case. You will see. This two-loop case was really tough. So now the general case. Now consider a general graph. So how does it contribute? Let's see. How does it scale? A general graph contributes as it contributes as what? So if I have a general graph, I have G string to the power of the number of propagators. So each propagator gives me a G string, propagators. Each vertex from the action gives me a 1 over G string, so minus number of vertices. Good? And every time I consider a correlation function of an operator, because I choose operators to normalize them by 1 over G string outside, it's my definition of my normalization, there's also minus the number of external operators, which we can also call insertions, number of insertions of operators. And what about concerning power of n? I have n, okay, to the number, what we call the number of faces, or which is the same as number of loops of color. Faces in the sense of this, if you have a frame and you see how many window faces, how many glass faces you have to put on your graph. So it's the number of loops, or in other words, number of closed lines. Okay? So this thing here, these propagators, let's call this L for lines. These vertices and external operators, normalized as they are, you see, this is why we normalize them as they are. Each of them is like a vertex now, because now vertices and external operators, they are not distinguished because both come with 1 over G string. So this is what we call V, which is not just vertices, it's vertices plus external operators. So if you want, you can write this as V internal plus V external, but this will never play a role, just to keep in mind that this V stands for all vertices of the graph now, internal or external. right? So in this case, for example, this could be a correlation function of 2 raised to t to the 4, or it could be a vacuum diagram. I would not have to distinguish because I'm normalizing external operators in the same way as I normalize vertices. Okay? And this is what we call this here number of faces we would call f. But now, in any graph, there is this statement, which is this Euler characteristic statement, that, or let me call this E for edges. This is how people normally state it. That the number of edges of a graph minus the number of vertices plus the number of faces is a way of counting the genus, the Euler characteristic of the graph. That's just a general statement. It's relatively straightforward to prove. If you want, I can do it tomorrow. I don't remember now. But it should be familiar to everyone, right? Is it clear? And therefore, these expectation values, an expectation value, takes a very nice form. I can always write it in the following form. I separate my graphs into genus. So I sum over graphs of different genus G. Okay? And then I can always write it as, there are several ways of writing. I don't know why I chose this one. I prefer this one actually here. As n to the power 2 minus 2 genus. If I factor out this, n to the power 2 minus 2 genus, which is what I need. You see, I replace faces by 2 minus, I replaced faces by there should be a minus sign somewhere. Yeah, here. Good. Thank you. So I replace faces by 2 minus 2 genus minus that, and then that combines exactly with that. Okay. Times a function times the sum of graphs all with the same genus. They all contribute with the same n. This is what we just established. So there is a function for a given genus that is just a function of the 't Hooft couple. Okay? And of course, let me point out that this is equivalent to saying that I sum over genus G. I put G string to the power 2 minus 2 genus times another function f tilde of lambda. Okay? Because I can either put n outside or G string. If lambda is fixed, it's the same thing. Okay? So what did we establish? We established that all graphs of planar topology scale like n square. All graphs of genus 1 scale like n to the 0. All graphs of genus 2 scale like 1 over n squared, and so on and so forth. And this is what we saw here. Let's check. So genus 2 here was 1 over n squared in total. That's what we get. Genus 1, we have two examples. This one, which is n to the 0, it's what we get there, and the other one up there. And genus 0, we had one example. It was like n squared. It's like n squared. But we just proved that it's a more general feature. If we decompose graphs into different topology, now we see that all this line scales like n squared. All this line scales like n to the 0, and so on and so forth. So I can organize my gauge theory expansion, my perturbation theory expansion, by a sum over different genus. Right? I sum over genus. They become more and more suppressed as I sum over genus. There is some parameter that I can call n or g string that is the same as I would do in string theory if I would have a string coupling, where I weight my sum over Riemann surfaces by a parameter that measures the number of holes in my surface, that tells me what's the probability for the strings to split. And then, for a given genus, I don't have just one surface, but I have to sum over many graphs. But that's fine, because also, in string theory, when I specify a topology, I have to integrate over all possible shapes of strings. So it's in this sense that we can say that this is, if you want, a definition of a string theory. Okay? So this, what we get here, is the usual string perturbation theory definition. where we take some external operators, we sum over surfaces of a given topology. For a given topology, we have to integrate over all surfaces. Okay? So this picture, one second. This picture, if this picture is correct, it is hinting at the following identification, that I should think of this GC as a string coupling, I've actually been calling it G-string for some reason. And we should think of this lambda, of this 't-Hooft coupling, which is G-string times n, as being related, this doesn't mean an equal sign, but related to the string tension. You see? So the idea, this will be precisely correct, the idea is that even if we fix a given topology, we need to sum over many surfaces. Okay? Which is, even if we fix a given topology, there is this summing over various surfaces where h bar is the string tension. If the string tension is very huge, you just sum over a classical solution. Otherwise, you have to do a string path integral over all possible surfaces. Okay? Yes?
When we're doing this large n expansion, the nice thing about it is as you increase in genus, you get smaller and smaller.
Yes.
But do we know that the number of terms doesn't, like, say, increase to a larger, like by a larger amount? Say if they were like, and if the number of terms in as I increase in genus was going, say, as n cubed, then
yeah, but you see, clearly the number of terms is a topological invariant of graphs cannot depend on n.
can't depend on.
Yeah, how could it depend on n, right? N, you just draw all your graphs,
Right.
and you don't know what n is. You just know what n is when you start summing over the loops and counting powers of n. So the counting of graphs, how many graphs there are at each genus, it's a good question. You should ask. How many graphs are there at each genus? Can it be that it becomes more and more complicated? But it can never be that the number of graphs of a given genus is dependent on n. The n is just, you just figure out the n dependence afterwards.
Just to be sure about this, I think it's actually vertices minus edges plus faces. I think there's a sign on the
So let's see. So I want propagators minus vertices minus faces. No, this should be correct.
It's order 0 minus order. It's like order 1 minus order 0 minus order 2. It's odd minus even, or even minus order 2.
What do you think is wrong? You think there is a plus here?
I think there's just an overall sign, but maybe on the left-hand side.
So let's see. If so this formula is correct for sure. So let's see. So V goes here, this goes here, and then I'll get to, no, it should be correct.
And usually the right-hand side is 2 times 1 minus 2 instead of this, so maybe you just don't see it. I think it's good.
Anyway, let's see an example. Well, let's see that it is working. Let's see an example that we did here, for example, this genus 2. So let's see if it works. So for genus 2, we had the number of edges, which was the number of propagators, was 7. The number of vertices, we said, was 4. And the number of faces, which is just the powers of n, after so much counting, we understood was just 1. And we get 7 minus 4 minus 1, which gives 2. And we are saying that this 2 was 2 times 2 minus 2. I don't think there is an answer. Okay. So the intuition is the following. The intuition is that you start summing over all these surfaces, but this here doesn't look yet like a smooth surface, these first graphs. But you could imagine that in this dot, 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 when I start considering graphs with 1 million vertices, now it looks very much like a dense surface. Do you agree? So the intuition, the basic intuition, is that as I start considering graphs of many, many, many loops, when I start considering a huge number of loops, and some crazy. I'm drawing a planar graph here, but with many, many loops. Now I'm not drawing a fat graph, but you see? Now it starts to look more and more from far away like a smooth surface. So, and this matches our intuition that if lambda is somehow related to the string tension, we expect to have some kind of classical string that we should not be able to see in perturbation theory, but only when the coupling is very large, which, morally speaking, is a bit like infinite loops. You have to really, really, really resum all the loops to start seeing some string that you have morally the right to call a classical string. So we expect a classical string only at very large lambda. Whereas at very small lambda, we expect a very quantum string, a string where the string tension is so small that nothing is obliging it to go along a geodesic, but rather it's just vibrating like crazy and so on. And you have really to sum over all string path integral. Okay? So we expect, so this intuition already hints that if there is some kind of duality between quantum field theories and string theories, it should be particularly powerful to study the strong coupling limit of gauge theories. This is good news, because it's the limit where we have no hopes of solving the theory typically. So this is great news. If this intuition will be correct, it will tell us that perhaps if we can make this precise, these string theories can come to the rescue and helping us study gauge theories in precisely the limit where typically our normal tools are not suited, which is when the coupling is very large. Okay? So that's the first comment. Now, the second comment is that these strings, we have this string coupling, and if n is large, the string coupling is small, so these strings are almost free. They just propagate, and they don't want to split or do anything like that. And in fact, we can see it even more clearly if we study scattering of strings. So let's suppose I consider two strings that are propagating. And if the strings are almost free, I should see that this propagation here is much bigger than the case where they interact. Okay? So let's see that this is the case. So this thing here, I would consider it as being the correlation function of 4 operators. 2 of them being these 2, and the other 2 being the final ones. Right? So each operator we think as a string, right? It's a trace, so it's a circular object like a spin chain, right? Like a circular object, going around. And then we have these 2 strings going into 2 strings. And what is this statement here? The statement here is that if you have any correlator, you can write this correlator as the disconnected part, right? We can always do this, plus the part that is fully connected. Right? So for example, suppose these operators are trace of m cubed. I can just disconnect the graphs and connect one operator to one and the other to the other, like product of these graphs in the first line, or graphs that are fully connected. Do you agree? But now see that graphs that are now these guys are fully connected, these are fully connected, and this is fully connected. But when a graph is fully connected, it scales like n squared, right? If it in a planar limit. So these first ones are of order n squared times n squared, whereas these second ones are just of order n squares. So this is both in the planar limit. So it means that exactly these graphs are much bigger, are indeed much bigger than these ones. These ones are much bigger than these ones by a factor of n squared. Indicating again that I can think of G string or n squared, as I said, they are equivalent because they differ by lambda, which is held fixed. That I can think of this n squared or of this G string as being a string coupling that is telling me how they are coupling. Okay? So this is very important. So this is called large n factorization. It's a general property of large N-gauge theories that if you want to consider multiple correlators, the leading term is when they become disconnected. And physically, in terms of string theory, this is equivalent to saying that strings are almost free. Now, it's very important to emphasize that free strings are not trivial at all. When we say a string is free, it means that they don't merge and split and so on. But they still vibrate. They still have some string tension, and they are still evolving in time. So its propagation and its spectrum and so on can still be very non-trivial. What we are saying is that the probability of a string splitting into two is very small. That's what we call being free. Okay? So in string theory, there are two parameters, the string coupling and the string tension. Right? So here we are talking about the string coupling. Okay? So, yeah. Another way of saying it, let me continue there. I want to finish making just a few comments, just this bottom part of the page, such that we close this general discussion and tomorrow we become more precise again. So another comment we could make is try to measure what's the coupling of this string. Okay? So how would we measure the some coupling? Let me just imagine we have, let me tell you how I measure this coupling. So I would say that if I want to measure the coupling of a string, say the 3-point interaction, O connected, I could do it. But of course, by itself is not very well defined, this object, because I can always normalize my operators however I want. I can multiply I decided to put operators with 1 over G string, but I mean, why? I could multiply them by n to the 10, each operator. So the proper thing to measure the interaction is this object divided by the normalization of my object, correlation function, this to normalize to the power 1/2. This will be a normalization of this guy. Then I need this one and this one to the power 3. This is normalization independent. But now, this scales as how? This scales as n squared over n squared to the 1/2 to the power cube. And this is 1 over n. So indicating once again that the coupling, the way I should think of the coupling, is it's not 1 over n squared. But it should be 1 over n squared. What did I do wrong? Is it 1 over n squared?
You've only got 3 at the top, so why should it be?
Ah, it's okay. Yeah, it's good. Yeah, it's good. So it's 1 over n. I could also normalize, I could also consider what about the 4-particle interaction divided by the normalization, OO to the 4/2. And I would see that this scales as 1 over n squared. Okay? So indicating that these couplings of strings are indeed very small. This is all re-saying the same thing several times. But let's see, for example, how this would match with some intuition from some kind of effective field theory of strings that are interacting weakly. Let's suppose, for example, these closed strings that could contain gravitons. Right? These closed strings could be gravitons. So let's suppose we just have some action for these gravitons, which would be some integral, 1 over G Newton outside, and then some fields here. Okay, some kinetic term and so on. So now what would we do to compute this interaction? For example, this 4.1. We would put something, we would draw some graph like this with some interaction, and we would divide by just the propagation, the free propagation. It's 2 propagators. So how would we say this goes? This goes, there are 2 vertices here. So 1 over G Newton square. There are 5 propagators here. So G Newton to the power 5. And here there are 2 propagators, G Newton square. So we would identify this with G Newton. Similarly, if I would try to measure this interaction versus just the free propagation, I would say that there are 3 propagators here. So G Newton cube and 1 vertex. compared with just one propagator. And I would say that when I divide, I have to divide by these 3 propagators, so times this one also. This propagator to the 1/2 to normalize this external guy. So here I would have g Newton to the power 3/2, and this would go like square root of g Newton. So we would indeed once more identify g Newton, the interaction, with 1/n squared. Okay? Once again leading to this interpretation. So this is just hand waving. It's not precise at all. I'm telling you that large N theories should be described by string theories, but it's a should be, and then which string theory? I'm not writing down any action, not writing down anything. I'm just arguing that it should be possible. This is how things started. When 't Hooft wrote his paper, he said that, look, large N gauge theories, they have this organization, graphs organized like this, that should be a dual description. It might be very hard to find it. We might try to say, what is this dual description for QCD? Do we know it? No, we don't know yet. But sometimes we know. For some theories, we can work out what is the precise dual description. But what these kind of cartoons are telling us is that there should be one. And this description should be such that strings are vibrating, and this vibration of the strings is related to the 't Hooft coupling. So we trade summing over many, many diagrams of a given topology by integrating over surfaces of a given topology. So that's a trade-off that we can argue whether it's good or bad. And I will argue that it's very good. Why? Because it's a 2-dimensional problem, string theory, whereas summing over all graphs is a 4-dimensional or d-dimensional in general problem, which is much harder. So it's a good trade-off. And summing over graphs of different topology would be like going to string theory in different topology, which is hard. Typically, you go and study string theory. When you scatter strings, if you start doing string loops, it's a tough computation. So people have been developing methods, but it's tough, but it's also very tough to compute these graphs. Okay? So this is kind of the moral of the story. And let me just finish by saying that large N gauge theories, in the last 5 minutes, we'll go a bit over time today, that large N theories are also spin chains. And they are also spin chains in a rather similar, by a rather similar argument. You see, when we have a single trace operator, right, which we draw like this, there are many pictures we can draw. But we see that what we have here, we have an object that is a 1-dimensional object. So this is a 1D object, which is identified at the end. So this looks like a 1-dimensional spin chain with periodic boundary conditions. Right? I have spin up, down, something like that. Now, in what sense? Let's try to be a little bit, at least a little bit more precise. In what sense? For example, I could have 2 types of matrices, M1 and M2. And then I could have, for example, I could have trace of M1, M1, M2, M1, M1, and I could say, let me think of this guy. Why not? I can. There is a map. It's isomorphic, saying up, up, down, up, up. It will be just my choice. Right? It will be a spin chain. It's just casual notation. I have the right to do it.
Down in the last spin.
Yeah, down in the last spin. Sorry. Good point. Yeah. I just identify M1 as being up, M2 as being down. It's just a notation convention that I just decide to do it. It's isomorphic. The Hilbert space of spin chains is the same as the space of single trace local operators. Why would this be something reasonable to do? Why would I decide to do it? Because suppose we have this kind of example and we start doing perturbation theory. So let's do it. Let's suppose we have this example where we have our 5 spins, 1, 2, 3, 4, 5, and I consider a 2-point function. Okay? Now let's study this two-point function of two such operators, which would be like considered an evolution of a spin chain. So let's take a spin chain and evolve it in time. So what happens? Well, the simplest thing that can happen is I just connect this by propagators. You agree? Or I could start putting some interactions that would come with some power of lambda. But what could these interactions be? For example, it could be this. I could have a cubic vertex there. Now all these graphs are fat, but I'm not drawing them fat. You should fatten all the lines if you want. Or it could be this, where this line goes and interacts with this one passing below the other one. But you see that the planar graphs, they are more important. So in perturbation theory, these graphs are more important than these ones. Okay? So what is happening is that the natural thing that comes out is, if you think of this as a spin chain, it's a spin chain where, to leading order, you have interaction between nearest neighbors. The kind of interactions that will naturally come out will be nearest neighbor interactions. So what this will lead to, we will see in more detail, is to spin chain Hamiltonians, when we study the evolution of these spin chains, that are of the form sum from n equal 1 up to L of some nearest neighbor interaction with some coupling lambda. But then as we go to two loops, we start putting another line here. So plus lambda squared times the sum of Hamiltonians that become a bit less local plus dot dot dot. Okay? So the claim will be that perhaps we can imagine the following awesome situation, which would be a situation where we would have a four-dimensional gauge theory, and we would be able to use techniques from spin chains to describe the gauge theory at weak coupling, because it's this notion where the first term is more important than the second term, than the third term, and so on. And at weak coupling, it will be the domain of the spin chains. And we could borrow all these powerful techniques that we have been developing. And then we would have this parameter coupling that we can increase. And as we increase, when coupling is very large, string theory takes over. And there we would use a description in terms of summing over strings. And what about in between? What in between? You can still use either of them. But then it will be the hard part. We would have either very quantum strings or very long-range spin chains. But that would be reality. And indeed, this is what we will see, that in some contexts, when we have the so-called ADS CFT or holography, we have some gauge theories that can either be described by gauge theories or by string theories. In some domains, gauge theory is dominant, and it's more simple to think in terms of Feynman graphs, and it will be the domain where spin chains will be important. And there will be another domain, which is the strong coupling domain of the gauge theory, where string theory takes over, and classical strings is what dominates. And then we will use methods more akin to the kind of classical integrability that we were using for this Landau-Lifshitz model, because string theory will become a classical field theory and so on and so forth. So both kind of techniques, like classical integrability techniques, will show up when we'll study strong coupling and be describing classical strings, strings with a huge string tension such that they move along classical trajectories. And at weak coupling, where we will see that our gauge theories will be mapped into spin chains, and then we will be able to borrow techniques that we have been developing for spin chains. Okay? And it's a fascinating thing that there is a total interpolation between these two different worlds. And that the full model that interpolates, it's neither a spin chain nor a sigma model. It's some hybrid object in between, which people are only now realizing what it is and how to properly study it and understand it at any value of the coupling. But this will start tomorrow. So, questions?
You have something short. Shut up.
It's a bit, so like when you have a matrix product state, the idea is...
No, I understand. I know what product state is. Yeah, I know.
Here it's a trace. So what's the relation?
There's no relation, I told you. I mean, there are many graphs. I mean, a fork also looks like that. And a fork is not related to matrix product state. I don't think there is a relation. I mean, this is also a product of matrices and so on, but in matrix product states, you do a variational principle to find the matrix and so on, and here you integrate over it. So, I mean, a priori, that's not an obvious relation, at least to me, but there might be cases where the matrix product states with many, many internal index perhaps can be approximated, but I'm not good enough with these slides. You should tell me later when we will learn more about this whether there is a deep relation or not. To me, I don't see one. An extra one? Good. So no. There is no extra n. Let's work it out. So here, remember that we normalize with 1 over G string here, right? So this graph, it contains 1, 2, 3, 4, 5 powers of n. So this is n cubed times G string minus 2 because it's the way we normalize the external states. This one is G string minus 2 from normalization. And now 1, 2, 3, 4, 5, 6, 7. So n to the 7. Right? 7. And 2 more G strings from the vertices. G string square. So in total, these 2 graphs, this one is just n to the 7. And this is this. So let's factor out, as we said, n square, because we want to. I did something wrong here. I forgot the propagators. Sorry. And then there are the propagators, 1, 2, 3, 4, 5. So G string to the 5. So in total, if I factor out n square, I get n square times lambda 5. Right? And here, I forgot also the propagators. So the propagators I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So G string to the 9. Right? So if I factor out n square, I get n square times n to the 5 G string to the 11 minus 2. Okay, it's easy. 9. Right? Sorry?
Here you get n cube lambda, n cube.
So Liz, you have your list care thing? Yeah.
1, 2, 3, 4, 5. No, you're right. Lambda cube. And here, I factor out n squared, I get n5 this. Is it correct?
Yeah.
Let's see if I did a mistake. 2 here, 2 vertices, and 1, 2, 3, 4, 5, 6, 7, 8, 9 propagators. It looks good. So I factor out n squared, and I get this, which should be.
So which is 9? So is this also a propagator?
Yeah.
There's some extra powers.
I'm doing something silly here. This is minus 2. Vertices come with the minus 2. Right? It's 1 over G string. So it's 5. Right? So you see, this is just lambda to the 5. It's not good yet. No, it's okay. Lambda to the 5, yeah. So, okay. That's because there is 1 power from here and 1 power from here. It's like a 2-loop diagram in that sense. So, okay, to the lambda square. But the point is that from point of view of power of n, it's still n squared, right? It's a planar graph, and it should be the same power of n, and it is. What's important is that by powers of n, they are organized in a way that. Now here there is lambda square. The way if we want to describe just a propagation, let's describe just a propagation. So let's leave this indices open. We just say we start with a state and evolve it. If I would leave this open, then I would remove this. So then I would say the counting would be easier if I would just remove this. Then I would say that how many powers of n there are here? Nothing.
Oh, okay.
How many powers of n there are here? 1.
Yeah.
And then there are, so let's repeat the counting in this language. It should give the same conclusion that they are of the same order, but the counting should be much easier to do. So now, if this indices here would be open, there are no powers of n. There is a 1 over G string from the normalization of this guy. and there is 1, 2, 3, 4, 5 propagators, but we amputate the propagator, say, so we also don't count this one. So this is just 1 over G string. And here it will be 1 over G string from the external one, which I also don't know why I count if it's the same. And then what I get, what the new thing is that I have 3 new propagators. So these 3 new propagators give G string cube. 2 new vertices. So I get 1 over G string square. And 1 new loop of n. And this is just lambda.
So should you consider this as a vertex or should you consider this as...
This thing here?
Yeah. Because now these are, like, all of these are open and this is kind of like drawing...
No, but again, it's important to distinguish that this picture here, I'm drawing it like this, but this is rather something like this, right?
Yeah.
This is special, this one. Here, it's really...
So it's like only 2 of these are coming and connecting.
Sorry, so this thing here,
Yeah.
there are 2 possibilities. Either these are cubic vertices, or if they are cubic vertices, then this is the counting. I could also use a quartic vertex here. And if I use a quartic vertex, then I have 1 less G string from vertex, but I also have 1 less propagator, so that I reach the same conclusion. So there is an expansion. From power of n point of view, graphs which are planar are all of the same order. But as I go to higher and higher loops, what I would call loops, they come with higher lambdas. So if lambda is small, I draw planar graphs without loops. Then planar graphs with 1 loop. Then planar graphs with 2 loops, but always planar. I don't stay out of planar. And because I don't stay out of planar, the kind of interactions that will generate will be nearest neighbor, next to nearest neighbor, next to nearest neighbor, and so on. Now I have to explain what is this H. I mean, I just draw something, but I have to now make this precise. But that will be what tomorrow we will do.
Is the point that the cylinder, if we remove the 2 points, then the cylinder corresponds to the Hamiltonian?
I did not explain what this Hamiltonian is. I did not define this Hamiltonian. It's impossible. I think it's impossible to understand from what I said what this Hamiltonian is, but tomorrow I will define this Hamiltonian.
But what does this diagram mean?
So the first diagram, when I compute the 2-point function, means a 2-point function.
Oh, okay.
In some gauge theory.
But the Hamiltonian is very complicated.
Now the Hamiltonian is related to this 2-point function. Now the precise relation within what is the relation between a 2-point function and an Hamiltonian, I will explain tomorrow.
What are these 2 matrices?
This will be, imagine you have a field theory which doesn't have just 1 matrix, but has 2 matrices. So I write an action, which is what I wrote, with M1, plus the same thing with M2, plus some interaction between M1 and M2. Right? Or in a gauge theory, it could be, suppose I have some matter fields, and there is 2 scalars. Right? Phi1 and Phi2. Then this will be the matrix Phi1, this will be the matrix Phi2.
Oh, so they're just 2 special matrices?
Just 2 fields of my theory, but they're not the same field. So if I have a large n theory, my fields are matrix values, right?
Yeah.
Then composite operators are products of these matrix valued fields, and at the end I take a trace to make it gauge invariant. Yeah. If I make product of different fields, then I get a structure which is a 1-dimensional structure with different objects at different sites. It looks like a spin chain already. And this would be totally useless if the interactions were non-local and so on, because then it is just a map of language. But it becomes useful because then the natural interactions that are generated are local interactions. So that's why it is useful to think of it as a spin chain, because we will have this notion of we have some 1-dimensional object, we put some excitations, they can hop a little bit, but they don't start hopping all the way and so on. Otherwise, of course, it would be, I can always do it, it's just notation, who can forbid me? But if the interactions, if it would be interaction, non-local interactions and so on, it would be a bit silly to go to this description.
But is this diagram in the same order as this diagram?
It's of the same order, but both are 1 over n squared suppressed compared to this one. So as long as I want to study large n theories, where I take the leading term only, I would drop both. Okay. I would keep this one, then I would keep this one here, and then and this one here, and so on. This is an interaction, not a line going through. I will keep all these graphs, but these graphs, for example, all these graphs here, now they come with the same power of n, but big power of lambda. Lambda is some big power. So if I am at a weak coupling expansion, first I want the terms in leading lambda, they are nearest neighbors. Then lambda squared, they are next to nearest neighbors. Then lambda cubed, they can be next to nearest neighbors, and so on and so forth. But provided lambda is small, I can truncate at five nearest neighbors, say, for example. When lambda is very big, then I have totally delocalized, everyone's interacting with everyone, but then the claim is that the string theory picture should kick in.
Yeah.
And then there should be a description in terms of smooth surfaces. Not spin change should not be the proper way of thinking about it.
M1 and M2 are just two matrix scales.
Two matrix scales.
So if there are more matrix scales, so that corresponds to SUN string change.
If you have more fields, you will typically get spin chains, which are more complicated than condensed matter spin chains, which are typically up and down. Now they can be SUN or SON spin chains, or they can even have fermions, so they will have spin chains with fermion degrees of freedom. And we will see that the most general case, we will get spin chains where degrees of freedom can be spins, fermions, and bosons can be on top of each other. It will be a spin chain where at each site, it will be a very rich spin chain that will contain a big particle content.
I don't understand how this identification, also what is this identification? But here you are right down from, is it an operator or? Operator. Operator, so this operator in some indication theory was stating. We don't operate the
Why not? Why? An operator is trace of M cube. Trace of M cube is an operator, right? It's a composite operator, trace of M cube. This trace is not tracing over the states of the Hilbert space or anything like that. It's not this average. It's just trace over matrix index. Just product of matrices, and then you take the trace of the matrix index. This has nothing to do with this trace. This may be confusion. This trace has nothing to do with integrating over M1 and integrating over M2. It's not at all related to this. This trace just means that I have M1 within this ij multiplied by M2 within this jk, dot, 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 and at the end I have M2 within this li. It is just this, this usual trace.
You mean this is an operator with indices 1 and 2?
No. There are two types of matrices, and each of them has two indices ij that I'm not writing.
Yeah, we are tracing those indices, right?
Yeah.
But also you're saying the indices are remaining are...
That's right. I will have a matrix, I will have a set of fields, MA, where A could run from 1 to some value, n, and then each of them is a matrix valued field that has two indices I and j.
So in this case, it's just 2 by 2 matrix.
This is just, there are two possibilities, two fields, but each of them is an n by n matrix.
Yeah, so we can write whatever object we want to write, and also some M1 and M2.
Yeah.
But so the length of this spin chain, well, I can write arbitrary.
Yeah. So I will have spin chain of arbitrary length. The length of the spin chain in this case is 5. If I stop here.
So what can we do? So when we draw this diagram, of course, this is already some many point function.
No, it's not a many point. What is the many point?
So when you draw this diagram,
when I consider correlation function of several single trace operators, this is a 3-point function. It's a 3-point function of 3 composite operators, but it's a 3-point function, the way to think about it. It's not a many-point function. It's like...
That just means some point function.
Yeah, so this would be a 3-point function, for
It just
example.
means this stands for some average of some corresponding.
Now the picture as it is, this picture I mean. This will be a 2-point function.
Yeah.
I have one operator here, and I contract both of them.
Yeah. So this identification is this operator to the state, but what about this correlation function?
So then you ask, what's the relation between this correlation function and the spectrum of some Hamiltonian? I have to tell you, there will be a relation like this. But this is what I will tell tomorrow. We will see that 2-point functions will be governed by spectrum of Hamiltonians.
So does that follow from this identification, or?
It will follow. It will follow, but it's not something I can explain in 1 minute. If everything was trivial, I would not be teaching. I mean, it's not 100% trivial. It's related to the renormalization of a renormalization group. I will have to introduce a little bit of RG and so on and explain how it works. It's simple in the end, but
So all kinds of, say, 5.1 version of it's not five sides.
well, it's not five-point function. Careful. You are thinking. I think you are. This is confusing you. The fact that you have trace outside, you are thinking of it as five-point function. This trace of product of 5m's, it's a one operator. It's one operator. It's not a correlation function of 5 operators. It's like composite operators. It's like in Ising model, you can have sigma or you can have epsilon, which is sigma square. You don't say that when you deal with epsilon, you are dealing with a 2-point function. You say epsilon is still a 1-point operator. And you can have either higher operators. You don't call them higher point functions. They are just operators. So this is one operator. There are many operators in the theory. What are all the building blocks? They are all the possible traces you can write of any number of fields, any product of matrices. This is like in the Ising model thing. I have sigma, epsilon, t. There is a spectrum of all possible operators. In large N theories, the natural spectrum to consider is take one single trace and consider all possible products. Then you can consider products of traces. Like epsilon times epsilon would be a composite operator in the Ising model. Right? If you put epsilon times epsilon at the same point, a normal order. That would be just one operator. But in large N gauge theories, product of two traces, it's a bit trivial because they're just factorized. So really the fundamental building block is single trace operators. Those are the building blocks that you should consider in large N gauge theories.